Welcome back, everybody. Welcome back to the channel. So, happy Friday, everybody. This is not going to be a typical video. So, this is going to be demo day, I think episode 3. This is going to actually be a series that I'm just going to make up on the channel where I basically just demo stuff on the programming language. Now, this is going to be a pretty chill Friday. It's not going to be that long of an episode. And this is a little bit different. I would have probably published a different video talking about how to build something in the compiler. However, I've been working my ass off on this feature like the past 2 weeks, and I just felt like this would have been a good time to talk about it because it's getting pretty close to release ready, and this may be in the next version, so we'll see about that. Today, we're going to be talking about fibers. This is going to be a new feature that's going to be in the programming language, and it's all about making concurrency real. Now, since this feature, the complexity of this feature is so complicated that I'm gonna try to figure out how I'm gonna show you guys how I did this. I'm probably just gonna end up doing a live stream. That's probably gonna be the easiest because then you guys can come in, you can ask questions and stuff like that. But this is a long awaited feature that I've been wanting to put into the language for at least 6 months. So I haven't figured out how to do it until recently, and let's just get right into it. So, what is a fiber? Fibers are basically another word for a green thread that allows you to basically add true concurrency when it comes to executing tasks in the programming language. So this allows for basically parallel execution on a single thread in the same way that you would get that running on multiple threads. So we'll see, that's pretty interesting. So we'll see how that works later on. And the word fiber is pretty much the technical term for the source code. Now, I'm going to be using a lot of jargon in this like presentation. Don't pay too much attention to that. These are just going to be a bunch of words that I made up, and they're the technical terms of the systems that I have in place in the programming language. So if you don't understand it, I will try to explain, but you don't really have to pay too much attention to it. But the word count comes from the idea that each thread, if you think of each thread as like a rope, right? And the rope is the thing that's holding you up, and each fiber is the individual tasks or all of the strings that make up the rope. Or if I wanted to bring up a better analogy, think of threads as like the frame of a car, right? So the thread is the ability to do work, right? So the threads would be the frame, the wheels, the transmission, everything else. And then the fibers would be the engine, the thing that does the work. So that's kind of how it's working. So that's kind of a general understanding of the system. Now let's talk about the problem. Like, why am I integrating this into the programming language? So first off, this came from me doing stuff on the drone project, and I had a common problem. Now, to make things a bit simpler, I broke this down into a simple program right here. So it's a couple of lines of code. And basically what this program does is I basically queue up 4 tasks that runs every second. And then I execute that task and I print out, the value. And then I also create another task that runs every 50 milliseconds. And I print out the value of that and I sleep the main thread for 2 seconds. So basically what's going to happen is I'm going to queue up a total of 5 tasks, and they each are delayed to a specific time. And the main thread is basically just waiting there, and it gives those threads enough time to execute. And then the main thread exits, and then all the other programs exit as well. So when you guys look at this, right, all of the 4 tasks that I'm creating, right here, basically they're running every second. And you can kind of see that I'm sleeping the thread for 250 milliseconds. So basically what's going to happen is I have these 4 tasks. As they're executing, they're going to all start at different times, but then they're going to sleep for 250 milliseconds. So the idea is that we should basically be getting the printout of all of these tasks after 1 second. Now, on the other hand, we have this task builder here where we're running this every 50 milliseconds. We do some work and then we print out 50. So the understanding is that this is supposed to run, every 50 milliseconds. So that's not the case though. So let's see what happens. So as you can see here, here's the actual output result. So we ran all 4 tasks first, and then we ran the 50 millisecond task, which is very bad. That basically meant that all of these tasks ran first and pushed the 50 millisecond task, or the last one, outside of its expected execution window. And the reason why that happens is because all these threads are sleeping for 250 milliseconds. And if you notice up here, I'm setting the thread max to 2. And what this does on my thread task scheduling API is it basically sets one thread aside for short-term tasks and another thread aside for long-term tasks. And these are all considered short-term tasks because I didn't specify them as long-term. So we're basically trying to execute all this source code on a single thread. And as you know, once you sleep, you basically block that thread until you get out of that function call. So this shows that instead of running this task down here every 50 milliseconds, it's actually running it every 1.05 seconds. So that's pretty much it. And then now let's try to solve this problem with a practical example. So suppose it's Thanksgiving and you and your family wanted to have some pecan pie for dessert. Now, how would you go about allowing everybody to enjoy that piece of pie, right? Do you fight over it? Do you kill each other? Do you make 4 or 3 additional pies for every other person? No, that doesn't make any sense, right? Obviously, you wouldn't make 3 other pies because you just spent all this time making this one pie. So instead of doing that, here's the obvious answer. Everyone gets a slice, right? So if there's 4 of you guys, everybody gets an even slice of the pie. So you guys get the point? Now, let's bring this back home with an actual code example. So this is now going to be the new software that's going to be on the next version. Now, I'm going to preface this with saying, before we get into the new software, if you guys have already written source code in Sharp, you don't have to change out any of this code. So if you're using the task scheduling API, you don't have to worry because all this stuff is going to have the new software integrated into it, so you don't have to make any code changes. So just keep that in mind. You still can use the new stuff if you want to directly, but if you don't really want to care about how it works and you just want to use the task scheduling API, you can still use this stuff indirectly in the next version. So now let's see how this works. So basically, what we end up doing is, now I still have this set thread max here. This doesn't mean anything at this point. This is just leftover code, so you can ignore that. But I create the same, 4 tasks, and then I create 4 more tasks of the 50 millisecond. Now, I probably should have created like, what is it, 20, because there's 20 50 milliseconds in every second, but whatever, you guys get the point. Basically, we're creating 4 separate tasks of 2 different things, and what we're doing is we're creating a slice. And basically what a slice is you're basically saying slice up the work to do something on this thread. You can see here that I'm passing in the current thread to the slice function, which means run all of this source code on a single thread. Now with the new source code, basically what ends up happening is we run or we execute 2 50 millisecond tasks, and then we execute the first task. Now all of the printouts are happening at the very end of the task. And it makes sense that, we're going to basically execute these 2 of these tasks first because basically they're finishing first because there's no delay. So we execute 2 of these, and then by the time we get to this task or the first one, the delay has finished, the task finishes, and then it prints out the result. Then we bounce back to the 50 millisecond task, and then we execute that, and then we bounce back here, and then we just keep bouncing around. So what this is actually showing is this is basically 8 concurrent tasks running on a single thread. And that's what's so amazing about this. So that's basically the new API, and this allows you to basically run all the code. So let's kind of see how this works, right? So I know this is kind of a lot of information. Basically, the old version, the way it would work is if we were to have our example where we wanted to submit all of our tasks, basically, the old version would create 4 tasks, or 5 actually, and it would try to execute all of them in 1 second. However, if you have enough of these tasks queued up, then basically they will push anything else outside of the 1 second time frame. So, and if you guys notice here, instead of calling thread.sleep, I am calling delay. And what delay does is instead of actually blocking the thread that's executing all the source code, it basically reschedules this task to be queued up at a different point in time in the future. So just keep that in mind. But you can see here that this is what happens, and this pushes the 50 millisecond task out of the 1 second window. And then now in the new version, what ends up happening is we execute both the first task and the first 2 tasks simultaneously all at the same time. And this, again, is all happening on a single thread. Then we pretty much process the second task and execute both 2 more 50 millisecond tasks, and then we, execute the last 2. So that's kind of how it works. It's kind of a basic understanding. And let's see. So why would we want to use fibers? Well, obviously, this allows for a massive improvement in terms of the amount of code you can run in the same time with using less resources. Now, when it comes to each type of thread, there's a difference in the amount of fibers that you can execute on each thread. Now, there's a philosophy that I have with this, that the idea is that the higher the thread priority, the less fibers you want to run on it. Because the idea is you're basically saying, I want this to be a high priority thread. So you want things on there to execute as fast as humanly possible. And based on the current way that the system works, there are recommended limits, there are physical limits, and then there are arbitrary limits. Basically, the physical limit of each of these, where I say max fibers here, this is literally the physical amount of fibers you can execute on a single thread with this thread priority in 1 second. So this means that you literally cannot execute more than this on a single thread in 1 second. Now, that doesn't mean that you can't have more than these amounts here, because theoretically you can have an indefinite amount of fibers running concurrently on a single thread. But again, these are just the recommended and the physical max barriers. Now, the recommended max is a conservative amount that allows you to basically balance performance as well as being able to run a bunch of code concurrently without really noticing too much performance degradation. Because as I'm sure you guys know, the more fibers that you increase, just like if you increase the amount of threads, the slower your program's going to be. So it works exactly the same. So let's go through the list. For high priority threads, you can have a max fiber count of 10. I only recommend you have 5 though, because then again, that performance versus degradation thing. For normal priority threads, you can have up to 14 maximum, and then I only recommend though having up to 7. And then for low priority threads, you can have a maximum of 40 and then a recommended max of 15. Now, if I go back here, I'm not setting the priority of this main thread here, but main thread usually starts with a max priority. So I'm already basically coming up to the limit here where I'm physically only allowing to execute up to 10 tasks per second. And you can see here that I have 8. So I have 4 here, which makes a total of 8. So if I go back here, so we notice that as it gets lower, the more fibers you can run. And again, the idea is that if you're running a low priority thread, that means that you're basically saying, I want the code to execute, but I don't really care when it finishes. It's a low priority thread, so just finish it whenever you get a chance. So that's why low threads can execute up to a maximum of 40 fibers simultaneously, which is pretty cool, right? Because previously this was not possible with the language. So let's talk about the types of fibers. There's two types, bound and unbound fibers. When it comes to bounds, there's pros and cons to each. So it's all about picking the type of fiber that you want to execute to fit your needs. Now, I will say that you can bounce fibers from different states. So you can make a fiber a bounded fiber and then make it an unbounded fiber and then switch it back to bounded again. It's not like once you create a fiber that you basically can't change it. So keep that in mind. But the pros for bounded fibers, basically you have controlled execution. So when it comes to bounded fibers, and by the way, these are like coroutines, if any of you guys didn't catch on to that. Just like in Kotlin, how it has coroutines and you can suspend them, unsuspend them, and pick which thread it runs on, this is exactly the same. It's just my own version. So you basically can select which thread you want the fibers to run on directly. And bounded fibers also protect against time slice loss. Now we'll talk about that in a second. They also protect against thread shutdowns if the main fiber exits. So basically, whatever fibers that are bounded to a specific thread, if you have, for instance, the main thread running, and then you bind like 3 other threads to the main thread, and then the main fiber that was executing exits, well, that main thread is not going to exit until those other 3 fibers have finished executing. So that's one of the benefits. You can look at that as a benefit or a downside. It just depends on how you look at it, I guess. So yeah. And as far as the cons for bounded fibers, basically the cons are that it's slower than unbounded fibers, and shutting down the executing thread if there's an uncaught exception kills every single fiber on that thread. So meaning that it basically runs on the philosophy of one bad egg spoils it for the bunch. So if you have 5 fibers running on a single thread and one of them crashes, they all crash, basically. So I was really fighting back and forth with how I was going to make this system work. But this is kind of what I have for now, and this is just the first iteration of the feature. So keep that in mind. But if you are using the task scheduling API, you don't have to worry about any of this crap. Like all this stuff that I'm listing here is if you manually try to use the fiber system directly. If you use the task scheduling API, you don't have to care about any of this stuff. So just keep that in mind as well. But when it comes to unbounded fibers, it's a little bit interesting. So unbounded fibers are definitely faster than bounded fibers. They're basically fibers that are guaranteed to execute all the time. They also do not shut down the executing thread if there's an uncaught exception. So if a fiber is not bound to a specific thread and it crashes, then it just crashes on its own. Now you will get a printout, right? So it's not just going to eat the exception and you just don't get anything. What's going to happen is basically if you run a fiber and it's not bounded to any thread and that fiber crashes, you'll just get an exception printed to the console and the thread will just continue executing as normal. I did this because it's not fair to the other threads that are binded to it if they're not all running together. So that's kind of my decision on that. It's also more scalable than bounded fibers. So when it comes to cons, it works as a catalyst to time slice loss. So let me talk about that for a second. So if you guys remember a couple slides back, I was talking about like the maximum amount of fibers you can execute per thread priority. And these numbers were derived basically from the time slices that I afford to each thread. So with high priority threads, the time slice is 100 milliseconds. The normal priority has a time slice of 70. And then I think low priority is like 25. I don't remember, but it's really low. But basically, once you do the math, what that means is that basically every 100 milliseconds, I'm switching the current fiber that you're executing to a different fiber to execute as well on that same thread. So I'm basically context switching fiber or green thread, for a lack of a better word, to a different green thread to execute. So that's kind of how bounded fibers work. But when it comes to unbounded fibers, they're basically like little thieves that run around stealing everybody's like time, basically. So unbounded fibers, the way it works is whenever the scheduler runs into an unbounded fiber, it does not care. It will literally find whatever thread is available to execute at the current time and just run on that thread. So that means that you can have an unbounded fiber run on the main thread, it can run on some other thread or whatever. Basically, there's no rules to what thread that the fiber can run on. And once it finds a thread to run on, it may not be on that same thread executing at the next time slice, it could be on a completely different thread. So it's basically stealing time from your entire application. Now that may sound bad, but in theory, it shouldn't be that big of an issue unless you have thousands of these things executing simultaneously, stealing time from your system. But yeah, so with that being the case, it basically requires you to have a lot more engineering work code-wise to make your program run efficiently. So I do have a way where you can basically, and I will go through an actual official video on fibers when we do a live stream. I'll talk about the API, how it works, and what you can do with it. But basically, there's a function that you can call. It's called fiber.poll, and you can basically poll a thread to see how many current fibers are running concurrently on that single thread. And those are only going to consist of the fibers that are bounded to that thread because that makes sense. That's the maximum amount. So there's little tricks that you can do to basically make sure that your threads are executing in a pretty decent manner. And I'll go through some of the source code in my task scheduling API that shows how I'm like basically using this new stuff. But yeah, so and another con to this as well is it does not protect against thread shutdowns due to the main fiber exiting. So because the fiber is not bound to any one thread, basically if the main thread exits, let's say I create a fiber on the main thread, but I don't bind it to that main thread. And if the main thread exits, well, then that fiber effectively dies because there's nothing to execute it. It's basically an orphan. So that's another thing you need to consider as well. But as long as the program itself is running, as long as the main thread is running, fibers only need one thread to execute on. So the unbounded fiber will basically, like I said, find any available thread that is looking to context switch to a new fiber. So there's that. Now, what about race conditions? So I know some of you probably are thinking like, well, okay, this is nice and all, but now I'm kind of worried, like, well, what if I have a race condition where I create like 16 different fibers on a single thread? And I'm manipulating some variable that is on that same thread, right? Because what if I try to use an atomic integer? Well, that's not going to work in this case, right? Because the way atomics work is you basically acquire a lock on the thread that has that lock. So if you're executing 16 simultaneous fibers on that thread, using an atomic integer will not help you because basically it thinks that it's a single thread and there's no point in like locking the object. So as you can see here, I have a basic example where I have this count variable. I create a slice, I run up to 10 million, I increment the count, I print out the value, and then I also, in the main thread, run up to 1 million, update the count, and, basically exit out of the main thread. Now, basically what happens is once the main thread finishes executing, it waits for this slice to finish because I bound this slice to the current thread. So this basically effectively becomes the main thread while this slice is executing. Now, what do you think will happen? So there's 10 million and then there's 1 million. Ideally, you should get the answer of 11 million. Well, let's see. we get the answer of 11 million. So when it comes to fibers, the way I built the system to execute all this stuff simultaneously, it basically runs at specific points to context switch the thread. So in short, to not get too nerdy on you guys, no, you do not have to worry about race conditions, which is pretty amazing because that basically means that if you had issues with race conditions in the past, using multiple threads, well, now you can just use fibers and never have to worry about that. Now, I will say that it has its limits, right? The fact that I'm executing all these fibers simultaneously means that if you're trying to like print data to the console, for instance, you're still going to have the same issues that you would have had if you were using multiple threads. If you were like trying to print hello world and then on a different fiber, maybe let's say you were trying to print John, you might get hello comma John world because the fibers are switching back and forth. So just keep that in mind. It's not perfect, but like I said, for the most part, no, you don't have to worry about this. So that's pretty much it for today, guys. This is a feature that, like I said, I'm really excited about. I'm doing tons of testing right now, so it's still kind of in the early stages. But once I kind of finish up adding in this feature, I'm going to probably do a live stream maybe sometime at the end of this month, where we kind of talk about how this stuff works and how to basically integrate coroutines, which is what this is basically, into your own programming language. So hope you guys enjoyed the video. As usual, if you have any questions, definitely put them in the comment section below. And until next time, I'll see you guys later.